So in this video, we're going to be looking specifically at solving problems using patterns, okay? And patterns are everywhere. We've got patterns in fabric, patterns on tiles, traffic patterns. Y'all know coming to the main campus, if if you are coming and you get here at 7:50 in the morning, between 7:50 and 8 o'clock, it's going to be a lot harder to find you a parking spot and even get off the interstate or get into the campus. So there's definite traffic patterns. We've got, patterns for TV schedules, and we have patterns in math. So does this pattern, is this a pattern? Does it continue? We've got a square, then a triangle and a star. Square, triangle, star. Square, triangle, star. We could keep going on with that pattern. I remember my children when they were in elementary school. I I just remember, I forget what grade it was, but I remember every kid would come in, they're like taking out the cups and saucers and forks and spoons and whatever, and they had to make patterns at their house. And so with objects. So that was their math lesson. That was their math homework. So patterns are going to happen no matter if you're teaching kindergarten or 12th grade. So we're going to learn how to recognize some patterns. So I just think this one is really cool. So if you notice, here's my pattern. I'm going up 1, 2, 3, 4, 5, but I'm multiplying whatever's left by 9. So I'm going to take 1 away. So I get 0 times 9. That gives me 1. 2, 1 times 9. That gives me 11. 3 plus 12 times 9. That gives me 111. 4 times 123 times 9. Do you see this pattern that's happening? This compared to this, this compared to this. Okay, so does this continue? Well, you would really need to get out your calculator to figure that out. And it actually does continue, but do you see where there might be a problem? What happens when you get to the number 11? When you get to the number 11, then you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops. I'm supposed to put a 10 here, but I only have one digit, right? So that's where it breaks down. But all the way up to that, it works. It's really sort of cool. Anyway, let's see if you see another pattern. And you may have realized this and used this when you were trying to memorize your nines. So here's our nines. 1 times 9 is 9. 2 times 9 is 18. 3 times 9 is 27. Okay, so here's our nines. Do you notice a pattern? Do you notice this? 1, 2, 3. Going up. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this one. And I could have put a 0 here. Now it even more matches 0 through 9 that way. And 0 through 9 coming up this way. I've had students that when they had problems and they couldn't remember their nines, they wrote that down. There's a finger, I'll have to show y'all in class the finger trick, but if you don't know the finger trick, it's really sort of cool. But anyway, so do you see that pattern? Also, what about add up all the digits? 0 plus 9 is 9. 1 plus 8 is 9. 2 plus 7 is 9. 3 plus 6 is 9. 5. Isn't that cool? Y'all are geeking out right now. All right. If you're just geeking out just a little bit, that means I might turn you into Math Geek yet. Okay. So that's a really cool pattern. So the question is there a pattern for 8? So we're going to use pull-out steps, okay? So understand the problem. Make a plan. So the plan is to figure out or to understand the problem. The problem is Is there a pattern for 8? So my plan. So let's talk about my plan. Well, first thing I'm going to do is I want to make sure I'm going to do what I did with these guys, right? I'm going to write out the answers and look and see if I can see a pattern. Maybe there's a pattern that does like this, going up and down. Or maybe I could add these guys together and get a number. So that's what we're going to do. Okay, so first thing we're going to do is write down 1 times 8, 2 times 8, 3 times 8, and write down our answers. So got our answers. All right, so now let's look. Ooh, this is looking good. 1, 2, 3, 4, 4. Uh-oh. It's almost good, but look, I'm not exactly because I got 2 4s there. Let's see. Look here. 8, 6, 4. Oh, goodness. It's going by. Now, that one is more of a pattern. 0, 2, 4. If I start from the bottom, 0, 2, 4, 6, 8, 0, 2. That's pretty cool. That's a cool pattern. But that's gonna sort of mess you up more than, over here you didn't have that. But here you would have to remember, oh, there's going to be 2 4s in there. Um, let's see about adding. What if I added these guys? I've got 1 plus 6 so I started off with 8. 1 plus 6 is 7. 2 plus 4 is 6. 3 plus 2 is. Hey, this is great. Oh, but then it messes up. It's messing up. But what if I add those guys together? If I add those, I get a 3. Whoops, I get a 3 and 2 and 1. So now, notice I've got a pattern. 8, 7, 6, 5, 4, 3, 2, 1, 9, 8, 7, 6, 5. It's cool. It's just, it's really cool. So there are some patterns. They're not quite as consistent as with the nines, but that's the kind of things that totally geek math people out. And then they want to say, now, why is there a pattern? Let's figure out why. Let's assign some X's and Y's to these things and start proving it. Anyway, that's what mathematicians do. Here's another one that's pretty cool. If you have real money, of course, y'all are going to be teachers, so none of us have money. But anyway, you could pull out a dollar bill. Give all your kids a dollar bill. Okay, could get expensive. But if you did, you could take out a dollar bill, and this is really cool. So if you have a dollar bill, take it out and write down. Oh, I should have done that, but I didn't do it on here. But write down the serial number, okay, and then mix up all the letters. Just write them up, mix them up, okay. So you now have 2 numbers. You've got the actual serial number and the mixed up serial number. Okay, you're going to subtract the smaller one from the larger one so that we don't get a negative number. Okay, so you subtract them and then you write the difference. And then you're going to add, so you would write the difference right here, and then you're going to add up all those digits, okay? And you're going to get a number that is 9 or bigger. If your number's bigger than 9, then add the digits of that answer like we did here. Like I added them and I got something that was bigger than 9. It was 2 digits, right? So then I'm going to add it again. Okay, and you keep doing that until you get down to one single digit. And that digit will always be 9. Is that not cool? Okay. All right, so that's a pattern. So now we are going to have fun with matches. Okay, now if you were teaching in elementary school, I don't know that you should bring in matches. You might want to do craft sticks, something that you can't burn, your kids can't burn down the classroom. But anyway, we'll call it fun with matches. Okay, so what we're going to do is we're going to look for some patterns, okay? So here we have 1 block. Now we have 2 blocks. Now we got 3 blocks. And they're it's like Cheez-Its, okay? Before we had, when we had our crackers in the last section, they were like Doritos. that you were lining up. These are more like Cheez-Its. And you could actually break out Cheez-Its and say, instead of fun with matches, you could do fun with Cheez-Its. Okay. So here's one Cheez-It. Here we put two Cheez-Its together. Here we put three Cheez-Its together. Okay. But now I want to know, but it's a little bit easier with sticks because of what the question is. So I want to know the number of horizontal sticks. Okay. So in other words, here's our horizontal, the horizon, like the beach, you're looking out at the horizon. So I've got two horizontal sticks when I have one block. When I have two blocks, let's count. 1, 2, 3, 4. So I've got 4. When I have 3 blocks, I've got 1, 2, 3, 4, 5, 6. When I have 4 blocks, get the idea. Okay, so that's our horizontal. Do you see a pattern? How would you go from 1 to 2, and 2 to 4, and 3 to 6, and 4 to 8? Think about that for a second. What would you do mathematically to these numbers to get those numbers? Multiply by 2, right? So we're going to multiply each of these numbers by 2 to get the next column. All right, and so that's the rule. So anytime they ask, what happens if I had n blocks? That's the way they say it. What if I had n blocks? That means you got to come up with a formula, okay, or a pattern. So now we talked about horizontal sticks. Now we're going to talk about our vertical sticks. So once again, we have 1. So I have 2 sticks, okay? But now when I have 2, I've got 1, I've got 1, 2, 3 sticks. When I have 3, I've got 1, 2, 3, 4 sticks. All right, so now we got to figure out what happens if I have n sticks. So I'm not going to look at these guys. Don't want to, so I'm going to not look at these guys, okay? I'm going to go from here, going to go from here to here. So how do I go from 1 to 2, and 2 to 3, 3 to 4, 4 to 5? Am I multiplying by 2 like I did the last time? Nope. It looks like what? Looks like I'm adding 1, right? Looks like I'm adding 1. Okay. So that's what we're going to do. We're going to add 1. All right. So now I'm going to not look at these guys. Man, let me go back. Don't look at that. Okay. So I'm not going to look at these guys. Not going to look at these guys. So I'm going to have, I was going to do the total number of matchsticks. So I can count all these. So I've got 4 there. I've got how many? 1, 2, 3, 4, 5, 6, 7. I've got, anyway, I could count all those. So I've got 4. So if I go, I've got to go from 1 to 4, 2 to 7, 3 to 10, 4 to 13. That's a little bit harder. So I'm going to give you a little hint, okay? So the hint is, notice each one of those I'm going up by 3. That means that 3n is going to be somewhere in my formula, okay? 3n is going to be somewhere in that formula. So here's a example. So if I did 3n, okay, and again, so if it's 1, it would be 3 times 1. 3 times 1, that gives me 3. Is that what I got here? No. I need another one, don't I? So it looks like I need to add 1 to it, right? Let's try it with 2. 3 times 2 is going to give me 6. That's not what I have here, right? I need 7. So I'm going to add 1 again. Add one again. Same thing with the next one. 3 times 3 this time. That's going to give me 9. Notice I've got to add 1. So each of those looks like my answer might be 3n plus 1. Let's see. All right, let me go back because I want to have all these guys. Sorry. I like to have all my answers when I finish. Okay. Is that everything? There we go. All right. So go up by 3s. So 3n plus 1 is correct. Now, if you had already known this, okay, if you already knew that and you knew algebra, you could say 2n plus another n is 3n and then say plus 1. But you know, your students might not know algebra, but this will be a great way for them to figure out what that's going to be. Okay, thought that was pretty cool. All right. Okay, so we need to talk about different kinds of reasoning. Okay, so we've got what's called inductive reasoning. Inductive reasoning is when you observe patterns and then you sort of predict the answers for more complicated problems. Scientists call this the scientific method. It's sort of like this. We observed our pattern that we had here, and then we got this rule so that we could predict, okay, if I have 12 of these blocks, what's it going to be, right? So that's sort of what we were doing here, okay? So that we could predict our answers for more complicated problems. Scientists call that the scientific method. Do you see why there might be a problem, though, with inductive reasoning? I'll give you a hint. You have to observe it. It's only based on what we can observe. So if we don't see something, then it's hard to do some reasoning with it, right? So anyway, so that's some negatives of the scientific method. It only takes just one example to show that your prediction is wrong. So this is called a counterexample. Okay, if you can't, so let's say I say, okay, I think that this is going to be 2n, but then I show something where, you know, I had 12 blocks and it was 3 horizontal sticks. Well, that didn't work, right? So if there's a counter example, then that proves, okay, that's not accurate. Okay, so I would need to go back and guess again, right, based on the patterns. Okay. If you can't find a counterexample, does that mean that prediction is always right? If I can't find one that doesn't work, does that mean that it's definitely right? That answer actually is no, because you may not have, just because you didn't find that counterexample, that doesn't mean that what you thought was true is actually true, right? So you have to prove it in other ways. Okay. Um, so here's some examples of inductive reasoning. Okay. It says if n is a natural number, remember what natural numbers are? What you naturally count with. So I call them counting numbers, but they're also called natural numbers. If n is a natural number, then n plus 7 divided by 7 is n. Is that true? Basically, can you just cancel those guys out is what it's saying. Okay. Well, hopefully y'all realize that that is not actually true. I call, in my math classes, I call this plus sign or a minus sign, I call it super glue. These guys are stuck together. You cannot pull them apart and just do it to one thing. Okay. There's ways that you can pull it apart. You can factor, You can separate into different fractions, but you can't just cancel stuff out, okay, because they're super glued together. So I've got to find me a counterexample. So I said, well, let's just start plugging in easy numbers. And I usually plug in zeros and ones and twos because those are easy. So I put in a zero and I see that I get, you know, one. So that's not true. If I plug in a zero, this is saying if I plug in a zero, whoops, this is saying if I plug in a zero right here, I should get a zero out. But I plugged in a zero and I got a one. So that is my counter example. Okay, because zero is not equal to one. All right, here's another one. If n is a natural number, then n minus 3 squared is n squared plus 9. So once again, we could plug in some numbers and see. Okay, there's some algebra that I could prove it to you algebraically, but let's just plug in some numbers. What if I just plugged in? I could try zero. If I plug in zero, 0 minus 3 is negative 3 squared would give me 9, and 0 squared plus 9, that gives me 9 equals 9. So I could put 0 in there and it would work. Okay, but when I put 1 in, look what happens. When I put 1 in, I get negative 2 squared is equal to 1 plus 9. That's not true, right? That gives me 4 equals 10. Well, 4 doesn't equal 10. So that is my counter example. So you would say the counter example, because on your test you'll be giving me counter examples. The counter example is where n equals 1, and this is what you get. Whoops, sorry. This is what you get when n equals 1. 4 is not equal to 10. Okay? All right, let's talk about deductive reasoning. So there's inductive, which is looking at those patterns that you've observed and making predictions. Then you have deductive reasoning. That's when you reach a conclusion by using a formal structure based on a set of terms and accepted premises or axioms. What in the world does that mean? Okay, basically, you're going to draw conclusions. You're going to prove things by drawing conclusions, okay? And once they are proved, then they're called theorems. Can you think of maybe a math class in high school where you did this a lot, where you had theorems and axioms and you had to prove stuff at the end? Maybe. Geometry. Now, geometry, I will say in high school, when I was in high school, my geometry was the majority of that class was proofs. When I taught it, none of it was proofs. I'm like, what in the world? Anyway, now, at least as far as I know now, it's a little bit more balanced. There's proofs and there's not proofs. But anyway, all that, that's called deductive reasoning. Okay, so here's an example. Okay, not in geometry, but maybe in the real world. So all Chevys are automobiles. All automobiles are four wheels. How about we say have? All automobiles have four wheels. So all Chevys have four wheels. Now you may say, Miss Kitts, not all automobiles have four wheels. Because my cousin Bubba, he's got a dually and it's got six wheels. Okay. These two are called, oops, I'll show you. Those two are called the premise or premises. Okay. And they are assumed to be true. True, even if you say, I know that's not true, Miss Kitts. Okay, the first two statements are assumed to be true. Okay, the last statement is called the conclusion. Okay, all right, so let's see if this is true. All all Chevys are automobiles. All automobiles have four wheels. Let's say that's true. Then all Chevys would have four wheels because they are automobiles. Okay. Um, so if statements 1 and 2 are true, then 3 must be true. This is said. Sorry, I'm having a hard time here. Okay. Then this is said to be valid. Okay. So this would be called a valid argument. Okay. It's a valid deductive reasoning. Okay. If something is not valid, it's called invalid. So not valid, fancy word is invalid. So here's one. If George Washington was assassinated, he is dead. So if he was assassinated, he's dead. Therefore, if he's dead, he was assassinated. George Washington is dead. He was not assassinated. So this is invalid. Invalid reasoning. All right. So let's decide if these guys are valid or invalid. So all cats are animals. This, whatever I'm holding in my hand, is not an animal. So therefore, what I'm holding in my hand is not a cat. All cats are animals. What I've got is not an animal. So therefore, this is not a cat. That is valid. All right. All candy is fattening. All candy is delicious. Therefore, all fattening food is delicious. Because you could say all fattening candy, but once you put in the food in there, that's what makes it invalid. All right. All mathematicians are eccentrics. All eccentrics are rich. So we have to assume these guys, okay? Therefore, all mathematicians are rich. So if those first two are true, then yes, all mathematicians are rich. It doesn't matter if these guys are true or not, okay? So you might consider me a mathematician. I teach math. I can assure you I'm not rich. So, but you can't look at this final statement, okay? You can't look at this, and say, oh, I'm just going to look at that. Oh, yeah, that's a true statement, okay? You look at this first, if those are true, and see if that's true, assuming that's true, is this valid or not? Okay. So on your test, I will give you things like this and ask you if it's valid or invalid. Okay. So now we're going to talk about sequences. A sequence is just an ordered arrangement of stuff, either numbers or figures or objects. It's a sequence of things. Okay. Um, so the patterns that we looked at where we had the rectangle and triangle and star, rectangle, triangle, star. Okay, that would be a sequence, okay, because it is an ordered arrangement of objects, okay? But let's talk about specific kinds of sequences. Okay, so the first one we're going to look at is an arithmetic sequence. And so to go from one number to the next number, so these are numbers. To go from one to the next, you're going to add or subtract the same number, a fixed number. Okay. And that number is called the difference, or it could be called the common difference. So I could ask you, what's the difference or what's the common difference? So this one, we're going to look for the common difference of these guys and then find the next ones. Okay. So to go from 14 to 21, how much do we need? 14 to 20. 14, you can use your fingers. 14, 15, 16, 17, 18, 19, 21. 20, 21, sorry. So that's 7, right? So to go from there, it's 7. To go from here, it's 7. To go from here, it's 7. To go from here, it's 7. So the common difference is 7. And then we're supposed to find the next three digits. So to get this digit right here, we just add 7. So that'll give us what, 49? And then to get to the next one, we're going to add 7 more. So to get from here to here, we add 7. And from there to there, we have 7. We add 7. So we're going to get 49, 56, and 63. All right. Look at the next one. What am I adding to get to the next? To go from 1 to 6? That's 5. 6 to 11? That's 5. So we're going to be adding 5. So our common difference, and usually I'll say CD equals what? Or I might say D equals what? Okay, so this one was 7. This one is 5. We're going to add 5 to each thing. And then to go from here to here, we add 5. So that's going to be what, 26. Then we're going to add 5. So that's going to give us 26, 31, 36. Last one, oh, look at this one. I'm going from 12 to 7. Notice it's going down. So now we're actually subtracting. How much are we subtracting? Yeah. So our common difference is -5. We're subtracting 5. And so I just keep subtracting. Okay, so I will ask you to determine if it's an arithmetic sequence. So you look to see if you're adding or subtracting. I'll ask you for the common difference, and then I'll ask you for the next 1 or 2 or 3 terms. Okay. Here is another way that you can learn about sequences. We're going to find the first 5 terms in the given sequence. The key to doing this is knowing that this first one, all of these, your n, notice all of these have n's in them, your n is equal to 1. So this is the first, this is the second term, this is the third term, this is the fourth term, this is the fifth term. So to get to these guys, that 2 would be plugged in here. Okay. To get to that one, it would be 3. To get to that one, you would plug in 4. So the first term, I'm going to plug in 1 into that. Let me go ahead and show you what that is. N squared plus 6. So that's 1 squared plus 6. So that's going to give me 7. Then I've got 2 squared plus 6. So that's 4 plus 6. So that gives me 10. And then I keep going. Then the 3 squared plus 6, 4 squared plus 6, 5 squared plus 6. Okay. I'm going to do the same thing with the next one, except I'm not going to square it. I'm going to take my n, and I'm going to multiply it by 4, and then I subtract 2. Once again, this one is the first term, so my n that I plug in is going to be 1. So I'll put a 1 right there. Okay? So when I do that, I have 4 times 1 is 4, minus 2, that's going to give me 2. And then 4 times 2, that's 8, minus 2, that gives me 6. And I keep going. The next one is 4 times 3 minus 2, then 4 times 4 minus 2 to get the rest of those. All right. Do the exact same thing. I'm going to get my first, remember that's my first term. So I'm going to take 1 and put it right here. And notice it's an exponent. So that's 3 to the first power. So 3 to the first power is just going to be 3. And I add 1, so that's going to give me 4. And then I'm going to take 2. Whoops, didn't mean to do that. I'm going to take this guy, put it in there. 3 squared is going to give me 9. And I add 1, so that would give me 10. And I keep going until I get all my answers. Okay, 3 to the third, you just have to remember, oops, sorry, let's go back. 3 to the third, you just have to remember 3 to the third, again, that's 3 times 3 times 3. So 9 times 3 is 27, and I add 1 to it, okay? Then the last one, once again, if I want to find this, that's the first term, so I put a 1 right there. So all of these are essentially plugging and chugging, that's what I call it. So I just plug in 1, 2, 3. So I'm either going to plug 1 in there to get the first one, then I plug 2 in there, then I plug 3 in there, then I plug 4 in there, and then I plug 5 in there. And that's how I get all those numbers. So I'll ask you to find the first so many terms in a given sequence, and I'll give you this formula, whatever that formula is. All right, now I want you to look at this Fibonacci sequence. Let's determine first, is it arithmetic? In other words, do I add to get to the next one? Well, notice here I'm adding nothing, but here I'm adding 1. So it's not arithmetic because it has to be the same, right? So it is not arithmetic. Why not? Because you're not adding or subtracting the same number. So what's the pattern? I don't know. Let's see if I can figure it out. Let's see. To go from 2 to 3, I'm adding 1. To go from 3 to 5, I'm adding 2. To go from 5 to 8, I'm adding 3. To go from here, I'm adding 5. Go from here to here, I'm adding, what am I adding? I'm adding 8. Whoops, sorry, my dogs. So I don't see anything in common, but I do see, you know what? Let me pause this and get my dogs to hush.